In this picture, we see an offshore wind farm, a power transmission substation in between the turbines. Basically, it contains transformers and a control room. These set of transformers, which are in the substation, are step-up transformers taking the kilovolts, which all the turbines in its neighborhood produced, step this voltage up and transmit it to another substation to do another stage of stepping up. The reason for the black line is to demonstrate a straight line, a row or a column of turbines. This is one type of wind farm, and it's a chessboard type wind farm, meaning rows and columns, 90 degrees. There's another type that is curved, and we will show it later. In this picture we can see a pile tower of the wind turbine. A pile tower basically consists of two sections. The one that is in the seabed, sometimes 25, 30, 40 meters inside, deep in the seabed, goes all the way up in a deep water, and about 10 meters, 5 meters, 7 meters above the sea level. And that's one part. The other part is the tower, the upper part of the tower, which is being inserted into. And then the turbine itself. This particular slide represents 10 European countries on the right-hand side, and the total generation of electricity using wind turbines. And a total of 4.6 gigawatt, which are basically being produced by more than 1,500 offshore wind turbines. They are all fully grid connected in 56 different wind farms across 10 European countries. 4.6 gigawatts are being produced by 10 countries in Europe. Out of the 4.6 gigawatts, for example, Denmark is 21%, and UK 50%. More than 9 gigawatts of offshore wind power has been installed globally, and it represents only 3% of the total installed power capacity today. 9 gigawatt is equivalent to 3%. Let's look at a top-level block diagram of offshore wind farm. Let's look at the various components. Still very much top level. On the left-hand side, we see the wind farm itself, the turbines. They go into wind turbine controller. This controller controls each and every turbine specifically, by itself, independently. Their output of all the total output, the combined output of all the turbines, go into a power substation. And there are several stages of power substation before it goes out to the transportation grid. First degree, they all step up the voltage. First degree is a low voltage stage, from several kilovolts up to 10, 11, 15 kilovolts. Then it goes few hundred meters or maybe 1 kilometer to another set of power substations, another step up stage of the voltage from, let's say, 15 kilovolts to 50 kilovolts. And it will go then to another substation to step up the voltage from 50 kilovolts to 200 kilovolts. And that's very high voltage. Goes to the transportation grid, transmission lines. We will discuss in deep what is a cable. We will see the content of the cable. That transportation grid runs 20 kilometers, 30 kilometers, sometimes 40 kilometers up to the onshore, where it meets a power station to step the voltage down. So we stepped it up in the offshore, we step it down to the onshore. Then after stepping down, and again there are several degrees, several stages of the stepping down of the voltage, starting from, like we said, 200 kilovolts down to 11 kilovolts, 15 kilovolts. It goes to a distribution grid and then distributed to the various customers. And again, in a top level electric block diagram, we can see several sections. Number one, on the right hand side, is the wind turbines. They are all connected into a mutual bus, and this transmission line goes to a set of transformers. This set of transformers receive medium voltage or low voltage, step it up to high voltage, and using a high voltage cable goes several kilometers until it gets to the shoreline, and from the shoreline it goes to before the shoreline it goes to high voltage grid. After stepping out from medium level to high level, we transmit the lines up to the high voltage grid, meaning high voltage substation, and then it goes kilometers until the shoreline. In this slide we can see various types and families of offshore turbines. On the left hand side, the horizontal, HAWT. The bearing and the drivetrain are represented by red dots. And in the HAWT, as we've discussed before in previous sessions, the bearing and the drivetrains are in the center up there in the knuckle. In the various types of vertical turbines, we can see where the bearings and the drivetrains are. The deep winds, the one in the middle, has its bearings under sea. It has an advantages or disadvantages, but it's under the sea. The FAWT-S and -C, the two on the right hand side, they are rotating floats and they have their bearing on sea level. Now, because vertical turbines receive wind from any direction as opposed to horizontal ones, they can easily float and change their position. Wind comes from different directions. Their efficiency is not dropped dramatically if their position is varied. So that's an advantage for the vertical ones. Being able to receive winds in all directions and able to install them floatingly on the water. And there's an aspect, a very, very important one, called crosstalk when it comes to offshore wind farms. Crosstalk is the interrelation, an energetic interrelation between one turbine and another within a farm. The reason that this particular wind farm is curved like in a banana shape is in order to reduce the effect of crosstalk. It's reducing the interrelation effects between turbines because of high and low pressure. When we have two sets of rotors, if they were in the same plane, if we'll have two sets of rotors rotating in the same direction but not in the same position, meaning that one blade will create high or low pressure as compared with the other blade at the same very second. So when we have two blades and two neighboring rotors or blades, they have high-low pressure gains that affect them together. That's called a crosstalk. One blade affects the neighboring blade, the blade of the neighboring turbine. Placing the farm in a banana shape reduces the high-low pressure that it is being generated because of the interrelation of neighboring turbines. Also, it reduces turbulences. When two turbines standing looking towards the wind and they are one in front of the other exactly and have a common line, the front one will create turbulences, which we call wake turbulences, that will affect the back turbine. The back turbine will not see a nice steady wind coming toward it by a lower level of wind in terms of speed and also turbulence. This is why we have to keep long distance between two turbines which are placed one in front of the other. The fact that we have a banana-shaped wind farm, as we see in this case, help us to minimize the total required water area, meaning that in the same area I'll be able to produce more power. The density of turbines can go higher. Because the area of the farm in this particular configuration is smaller, we can actually minimize or shorten the distance between the turbines and the control room and the substation, and obviously the distance to the consumer end. And this is another family of offshore wind farms. It's called chessboard family. As opposed to the banana shape, we have a chessboard, X and Y coordinates. Turbines are placed in straight lines, straight rows, and straight columns. But in order to assure no wake turbulences, the distance between the front row and the back row and the turbine to another turbine on the right and turbine on the left should be 5 times the diameter of a turbine. Keeping this 5D in mind, enable to produce or to establish a chessboard offshore wind farm with high efficiency. The drawback of that, because of the long distance of one turbine to another, means that the entire area of the park will be very large, meaning that there will be longer cables, meaning that the substation will be far away from several turbines in the farm. But from a technical point of view, it's easier to draw straight lines and to run with turbines along it. But it has its drawback.